Hi, everybody. I'm Ryan Gross, and I am here to talk to you today about reinforcement learning that I think is going to become a huge part of our business over the next few years, not just in the consulting industry, but in all of our clients' industries too. And to reinforce my point, there's another talk on reinforcement learning today by another Ryan Kuiper. Encourage you to go watch that Alpha Zero talk as well. So, this past June, I had the opportunity to attend the AWS REMARS conference, which is a conference that focuses on a confluence of technologies, machine learning, automation, robotics, and space, and how those are going to come together and make a groundswell of capability around AI that is going to really change a number of industries over the next few years. So I want to walk you through a few of those so we can all get on the same page, get in the same mindset around the state of the art of the possible. First one is a company called Boston Dynamics. They've been working on smart robots for the past 10 years, and they are really building out this capability to do human-like tasks and superhuman tasks with robots. So what you're watching here is not CGI. This is a real robot being filmed in slow motion, and it is jumping up a set of pedestals trying to get to the top. Now, that robot had to actually adjust side to side as it lands and it senses the force of itself coming down. It has the body lean. It needs to adjust for that and push off to get up to the next pedestal. Now, what's even more interesting here is not only was that robot doing this one fixed task, but it was using a video image of what it was seeing to determine where those boxes were and be able to complete this same task. Even if you were to move the boxes around, make them taller, make them shorter, it will adjust for that. Another great example that we saw there, this was Amazon, so they had to talk about the Amazon Go store. Now, Amazon Go stores exist in many of our markets, and hopefully some of you have been to one. It's a really magical experience. You walk right in through the gates up at the top, you see these people walking in. This is an overhead view. You walk in, grab some stuff off the shelves, walk right back out the door, and you're charged on your cell phone maybe 15 seconds later. So they have to track these hundreds of people in the store. Maybe you see down on the left, you see people right next to each other who are looking on the shelves and picking out an item, so you can see those people in a real view here. They are needing to deal with a situation where it's really hard to tell who actually grabbed what with accuracy that impacts the bottom line. Another example that I think many people are familiar with is self-driving cars. So here's a car driving in the city of Pittsburgh from a company called Aurora, and it's trying to take a left turn across traffic while other cars take right turns, and it needs to wait for a bunch of pedestrians who are crossing the road to find that gap and then drive through it. So not only does it have to do that in a way where it doesn't hit a pedestrian, which is obvious, but it has to do it in a way that's going to feel natural to the people who are sitting in that car if people are going to actually start to buy these smart taxi rides. So these types of problems kind of have a common theme to me. They all really focus on these areas where if you needed to solve this using human beings writing code to simulate or to calculate every scenario, it would take a team of 100 people 100 years to get this right. And not only is this happening in those examples, those are barely even scratching the surface. We've got examples in healthcare with radiology dosing. We've got education with personalized tutors. We've got trade execution timing in financial services, and we've really got something happening in just about every industry. It's all nascent right now, but it's moving forward fast. So my conclusion coming out of this conference was that this concept that underlies all of these advancements, concept called reinforcement learning, is going to dramatically change a number of industries over the next N years. And I think, N is probably like 5, not 50. So the statement I have on the screen here is if the tasks in a field can be accurately simulated, reinforcement learning will dramatically improve the state of the art in that field over the next few years. So let's walk through why I think that statement is true and take a look at how reinforcement learning works under the hood to make that happen. So what you see in the background of this slide is a rat in a maze with some cheese, something you may have seen before as you were learning about classical conditioning or reinforcement learning in the more generic sense. So this isn't a new concept to the world, it's just a new concept to AI. In this world, or in this version here, the rat is what we call an agent. So an agent is what you are training when you build a reinforcement learning model. That agent really consists of two components. First, in order to actually learn things, it has a machine learning model in the traditional sense of machine learning that is attempting to learn the relationship and be able to predict the rewards that will be given to it based on what its actions lead to in the environment. So in this case, the maze is the environment, the cheese is the reward. The second component of this is around optimization. So within a maze, there's going to be many decisions that need to be made, and eventually you get to the ultimate reward state of getting to the cheese. But there's a lot of fast ways to go through the maze and a lot of really slow ways to go through the maze. So if you end up choosing a path that goes winding all the way through, maybe you get less rewards than if you go straight to the end result. And so optimization component tries to find the best ways to solve the problem. So let's take a look at how that works. You start out with an agent trained with a random model. And I have 3 young daughters. I think that this agent is really like a brand new newborn, having no idea what actions lead to any type of reward, what's good, what's bad, what's up, what's down. And so how do they actually learn, and how do they grow into being able to complete complex tasks like driving a car? Well, they do it basically the same way that a human baby does. They take an action, and they kind of observe what happens, and then they adjust. So in a lot of cases, you start out watching these reinforcement learning models in early stages, and they're like this robot on the right-hand side of the screen here. And they immediately just take that first step and fall down. They likely are in a simulation, so it's okay, they don't break. You just start another round of the simulation. So what happens is that step that they took was simulated in the environment. The action leads to some sort of physical response. The robot falls over. Sensors record that information, so virtual in the simulation, physical sensors in the real world, and they provide that back to the agent. So, okay, you are now starting to fall over. You need to take your next action. So then the model, with the optimization model within the reinforcement learning agent, then chooses the next action. And most of the time, what it's going to do is it's going to choose the action that maximizes rewards according to its machine learning model. So that leads to this concept where it can specialize pretty quickly on optimal ways to solve the problem. But there's lots of other ways that might exist. And so we need a level of curiosity in these agents. So sometimes it just takes a random action to see if maybe there's another space, another path down that maze. That right turn leads to a quick exit. And so once that is done, the next step is to really provide the reward back. So this is the part where human beings actually encode the rewards for the agent based on the actions that they're taking. So if the results are positive, if you get the cheese, that's the obvious one. But if you get the cheese faster, that's good. We can reward you for the speed at which you were running through the maze. We can also reward you for getting closer to the cheese than you were before. And those help shape the agent's behavior, because if it's just a go or no go, the agent's going to randomly run into walls for a long time before anything good happens. Now, what we just looked at was one loop around the reinforcement learning, right? It was just one step in the process. I'm going to switch examples here because I think it helps elucidate the real process of actually training a reinforcement learning model. And that's those actions. In the basketball example we've got on the screen here, an action could be shooting, it could be passing the ball, it could be driving further into the lane. Those are one action. You've got 60 minutes of actions that make up a game. We call that 60 minutes an episode within reinforcement learning. So everything that is done leads to some set of rewards, the number of points you scored in the game and whether you won within one episode. Now, you could have just gotten really lucky and you win the game and you score 100 points because your opponent had a really bad day and they just weren't playing defense at all. And we don't want the agent to learn based on these anomalies. So what we do is we actually batch lots of them together. Think we got a whole season's worth of games before we actually go update, or we've got at least a month's worth. And so then your model, the machine learning model that we're talking about that tries to predict rewards based on the actions taken, is using the average across all of this information, making it learn from statistically valid results as opposed to anecdotal results. And of course, because within this example, we're using reinforcement learning, of course, reinforcement learning has been trained to shoot basketballs with NBA level accuracy. The basketball example is also really interesting because Michael Jordan and Malcolm Gladwell really popularized this concept of the 10,000 hour rule. So we actually teach this to many of our Finns. If you've taken the deliberate practice or you've gone through drop training, you know about how 10,000 hours of deliberate practice can lead to mastery of a skill in human beings. Well, I found this really interesting fact about reinforcement learning based on the OpenAI 5, which is one of the most famous examples in recent memory of AI agents becoming superhuman at a given task. So OpenAI is Elon Musk's AI company. They trained 5 agents to play a game called Dota. We actually have many folks within Pariveda that also like to play Dota. It's a team-based, complex game, and those agents were able to beat the world champion players in 3 consecutive matches where the games were never even close. So really, the OpenAI 5 are the current world champions, undisputed, in Dota. But what I found really interesting is that in order to accomplish that, OpenAI trained those agents for 10,000 years worth of simulated playtime. So the key here is having that simulation available to you, because otherwise you're never going to be able to do 10,000 years of training in a real world scenario where the one game and then the next game are simulated. You need to simulate in parallel. So actually, those OpenAI 5 were trained over a period of about a month to play 10,000 years worth of time during that month. So with that, what are the requirements for actually building out reinforcement learning models? How does this get a little closer to something we could talk to our clients about? Well, first, you need an environment that can be simulated like we were just talking about. You're never going to hit the 10,000 year rule if you can't actually simulate the outcomes in parallel. Within that simulated environment, you're going to need a goal that can be precisely stated. So the precisely here means a mathematical function between the things that you measure and provide to your agent and the rewards that you return. So everything you measure through a bunch of math spits out a number that could be like the points that you're scoring in that basketball game or the points differential in your basketball game versus your opponent. The next thing you need is a discrete set of actions. So within a basketball game, each player can fluidly move and make fakes that other players, causes them to fall over. But in order to make this a computationally feasible process, there needs to be a set of actions. So instead of having a full fluid set of shooting, it's like ready position is one. Here is a second action. This is the third action. Similar things for passing the ball. You need to be able to have 1 through n actions to choose from. The fourth key thing for certain areas is really that ability to take this and bring it to the real world by having sensors measure the things that you were simulating in the simulated training environment. And that could be physical measurements using IoT, but it also could just as easily be a pure digital thing. So financial services, transactions, there's not really a physical element. A lot of things in healthcare are finding the best treatment plan, or things in education finding the best learning plan. You don't need a fully instrumented IoT apparatus to get moving on something like that. And then the last thing you need is a lot of computing power. So you have Google and Amazon and Microsoft really pushing the limits of what's possible with reinforcement learning frameworks and simulation environments because they want to sell you all of the computing power to train these agents for 10,000 years. So I do want to hit one more time on the simulation here, because I think we have a lot of folks within Pariveda now who really understand machine learning. And if you're looking to get into it, there's lots of other talks today at FinFest that you can go watch or watch later on to bring up your understanding of machine learning. And within all of those talks, at some point, they will talk about needing to build the right data set that is your training set or your features for your machine learning model. And they talk about that has to be cleaned and just right, and that's the most important, most time-intensive part. Well, for reinforcement learning, building that simulation is like building that training data set. That's where you spend your time, is getting that part right so that the rest of the process can use the algorithms to build that optimal agent for you. Last thing I want to hit on here is that reinforcement learning is not a silver bullet. You shouldn't be thinking that all problems that we come to in the future are going to be solved by reinforcement learning alone. So a couple of things to look out for. If you're thinking, oh, I can build a simulator based on taking all of the history of what's happened based on all of the inputs that I have, what you've really discovered there is a problem that can be solved very quickly using traditional machine learning methods. So great, go back to your client, talk to them about how they can use machine learning to start to get business value. The second thing is, if you've got a simulation where there's really only two steps, you've got a maze and it's only just one right turn and then one left turn, and then you get to the result, well, you can reduce that basically to a data set and use traditional machine learning methods there as well. So you don't need all of these advanced simulators in order to solve those types of problems. So great. Now we've gone through a lot of the concepts behind it. How do you actually bring this to your client? Well, the first thing to do is work through a set of questions with your client. So first, what are they already simulating in their business today? Well, if they're in an engineering company, they build products, they probably already have simulators for wind tunnels and physical properties. Oil and gas, very similar concepts around the flows, chemical processes, those sorts of things. If that's not available to you, or to look in broader areas of your business, you can take a look at what tasks can be completely measured end to end in terms of the results. So in my point of view talk, I focused on a company called Gong.io, and interestingly, I was actually on 2 calls today that were recorded by Gong.io. So what they do is they record the entire sales call and basically the entire sales process, reduce that to data, and they could then build a simulator where an agent takes the place of the actual sales person, and the results of the sales calls are starting to simulate based on an agent being the customer and an agent being the salesman. The next one to look at is which subtasks. So, okay, maybe we don't have everything can be measured end to end, but some parts of our task can easily be measured. So the financial services example I talked about before was Chase Bank, and a system that they were building in order to be able to not choose the right stocks that are going to go up and make their portfolio grow over the next 10 years, but choose the right millisecond within a 1-minute period to give themselves a maximum bid-ask spread profit. And so they used that across all of the trades that they're executing, and they ended up making millions of dollars of pure profit based on that type of agent for a very small component of their overall flow. So finally, once you've kind of thought through what can be simulatable in your environment, you need to start to figure out what training method you can use. And the best things to look for there are where you can kind of pit one agent against another agent. If they're playing the same game and you're just trying to have them compete, that's your ideal state. But if you've got that Gong.io salesperson agent, customer agent interaction, that's another one that could be used in order to hit that 10,000 year rule very quickly in parallel. So not everybody here is thinking, okay, I'm going to go talk to my clients on reinforcement learning tomorrow. So the last thing I want to hit on is, what should you do next? Well, if you're on the technical side and you want to understand really how to get into reinforcement learning, go watch Ryan Kuiper's talk, whether that's today or down the line, in order to understand what frameworks and languages you'll actually be programming in. Some of those that we can cover here today briefly are AWS RoboMaker for making simulations very easy to design. AWS SageMaker Reinforcement Learning, which packages up all of the technology you need in a click button form using a technology called OpenAI Gym underneath the hood. There's also DeepMind's open source libraries that they've just recently released to give you a lot of that gameplay, computer game environments to train on. And finally, there's the AWS Deep Racer that many of you who have gone through our most recent iterations of Developer School may have already raced on a physical racetrack. This is actually probably one of the best packagings I've seen of everything you need to do reinforcement learning, not only in the simulator, but translated into the real world. And hopefully there will be more to come once AWS starts shipping more Deep Racers out to the world. And with that, I'm looking forward to continuing the conversation with you. Thank you very much, and have a great day.